Another article that has used dual decomposition is again for dependency parsing, but this one for non-projective cases, because for non-projective I mean these arcs cannot cross, so this one is not allowed. So how can we work on dual decomposition? You see, there are lots of algorithms for dual decomposition. For example, lifted generalized dual decomposition by a different group, of course, and this one is also by a different group. But let's see the motivation. So as I said, unlike loopy belief propagation, our method has strong theoretical guarantees. You know, you are just hopeful that this converges. But in mathematics, we should measure what hope means, and we should measure everything. So we go to scientific things like linear programming, duality, symmetry, and those things. So for arc-factored models, as I said in the previous 2 or 3 lectures, we want to maximize, we want to find the optimal parse. And this is a kind of structured prediction. And so more complex scores, we need more complex scores to capture sibling dependencies. So one of the contributions of this paper is writing f of y as a different form, which is more general. When we say approximation, it means that Z here could contain cycles, because in dependency parsing, you should not say that, of course, a head can have 2 different dependents, but a dependent cannot have 2 heads. This is one kind of constraint. Another constraint is that this can never happen. It cannot be like this, that this never happens. And many of these constraints, and so we want to know that how can we deal with these situations. So we will see that dual decomposition can effectively use minimum spanning tree inference to rule out, rule out ill-formed structures like this, because we don't want to have loop in a tree in our dependency parsing, or different combination of arcs that may happen that we don't know. For example, some people, of course, that's a different topic. So sibling decomposition assumption, it assumes that it is possible to compute this value in polynomial time. And also the bigram sibling models that decomposes f, your score can be decomposes like this. And you will see why this is important, this is useful. So the height automata consists a second important model type that satisfies the sibling decomposition assumption. And these models make use of functions or variables in a set of variable states. And so what is the parsing algorithm? This is different, this lecture is different from the previous and lecture 4, because here we are formulating dependency parsing in some unusual way. So the article, I like the article of Andrew Martins because it's more natural, but this is another way you can formulate it. But both of them say that these constraints should satisfy. And so the master talks to the slaves, but in a different way. So from appendix, you know that what is gamma that I have shown here, because you write h of y, this one, as a linear combination of y. So without this constraint, the objective would decompose into separate maximizations, which can be solved solved easily using dynamic programming and minimum spanning tree. So it is these constraints that complicate the optimization, just like previous lecture or before that. Our approach gets around this difficulty by introducing new variables that serve to enforce agreement between y and z. And first we introduce the Lagrange multipliers, and we define the Lagrangian as this form. So we make sure that this is equal to 0, and this is our Lagrangian. And like any dual objective, it should be just function of your u is your dual variables, just like any dual optimization approach. So you write it as this is your dual problems. And when we say decomposition, it means that z and h are decomposed. They are not coupled with each other. And it is simply, you can write the subgradient, can calculate that, you can see for yourself that this becomes the simple subgradient, and you can use for this algorithm. So we are minimizing the dual. As I said, it should be related to the Lagrangian multipliers, so use our Lagrangian multipliers. This is the subgradient that you calculated for yourself, and we want to minimize our dual problems. It's like maximizing the primal problems. And you see that this one is just we maximize that. This is the y and this is the z optimization, and we iterate all of them until convergence. And we model the grandparent dependency model like this. We call it grandparent sibling decomposition. This is another assumption, that we assume it is possible to compute this one in polynomial time, so it's very efficient. After that, we can do the dual decomposition, and we solve y, we solve z, and these dual variables in order to for the algorithm to converge. And we use the discriminative linear models, and the score for a parse y is just linear. And so this algorithm is like previous algorithm, but with a different formulations.